Hi guys, this is the EdExcel A-Level Further Maths Paper 1 covering the core pure content, and it's from the October 2020 series. Question number 1. We have f of z which is equal to 3z cubed plus pz squared plus 57z plus q, where p and q are real constants. And given that 3 minus 2 root 2I is a root of the equation f of z equals 0, we have to show all the roots of f of z equals 0 on a single argand diagram. Because we've got a cubic equation, we would have 3 roots: alpha, beta and gamma. For part A, we already know one of the roots, alpha. That's equal to 3 minus 2 root 2I. Our other root, beta, will be the complex conjugate of this root, which is 3 plus 2 root 2I. And our third root, gamma, that's going to be of the form x plus I y. We don't know x and we don't know y, but we can find out x and y by considering the sum of the roots, the pair sum of the roots, and the product of the roots. Now, before we figure out the sum, the pair sum and the product of the roots, we would have to state the values of a, b, c and d. You can see here a is equal to 3, b that's equal to p, c that's equal to 57 and d that's equal to q. So for the sum of the roots, alpha plus beta plus gamma, that's equal to minus b over a. So minus b over a, we have over here minus p over 3. Okay. Next, for our pair sum, we have alpha beta plus beta gamma plus gamma alpha, that's equal to c over a. So we have over here 57 over 3, and this is 19. And finally, for the product of the roots, alpha beta gamma, that's equal to minus d over a. So we have minus d, so we have minus q over 3. Okay. Now if I call this equation 1, this equation 2 and this equation 3, we can use equation 2 over here to find out what x and y are, and then from that we can find p using equation 1 and q using equation 3. And the reason I want to use equation 2 to find x and y is because the pair sum over here contains no unknowns on the right hand side, whereas the sum and the product contain unknowns p and q on the right hand side respectively. So we will now use equation 2 to find x and y. So from equation 2 we can see over here we have alpha, beta, so we have 3 minus 2 root 2 I times by 3 plus 2 root 2 I plus beta gamma. So we add on 3 plus 2 root 2 I times by x plus iy plus gamma alpha, so we add on x plus iy lots of 3 minus 2 root 2 I, and all of this is equal to 19. So if we expand all these terms, of course we can just use our calculator. Make sure you're in complex mode. So to access complex mode, press the menu and then press number 2. So here we have 3 minus 2 root 2 times by I, lots of 3 plus 2 root 2 times by I. It turns out here we get 17. And if we expand these two brackets, we have 3 times by x, so that's just 3x. Then we have 3 times by iy, so we have 3y I. Then we have 2 root 2 I times by x, so here we've got 2 root 2 x I, and then we've got 2 root 2 I times by iy. Well, I times by I squared, that's minus 1, so we have a minus 2 root 2 y. Okay, and then for the bracket over here, we've got x times by 3, so that's 3x. And then we've got x times by minus 2 root 2 I, so we've got minus 2 root 2 x I. And then we've got iy times by 3, so that's plus 3y I. And then we've got iy times by minus 2 root 2 I. Well, I squared, that's minus 1. And then we've got this minus over here, so minus and a minus give a plus. And then we've got 2 root 2 times by y. And all of this is equal to 19. So if we simplify all of this, hopefully here you can see that the 2 root 2 xi and the minus 2 root 2 xi cancel. Hopefully you can also see that the minus 2 root 2y and the 2 root 2y also cancel. So tidying all of this up, we have 17, now 3x plus another 3x, that's 6x. And then 3yi plus another 3yi, that's 6yi. And all of this is equal to 19. And to find out the values of x and y, we can compare real and imaginary parts. So, if we compare the real parts, we have 17 plus 6x, and this is equal to 19. So we've got 6x, which is equal to 2, and therefore x is equal to 1/3. And if we compare the imaginary terms, on the left hand side we have 6y of them, and on the right hand side we have 0 of them. So therefore y is equal to 0. And knowing the value of x and y, we can therefore conclude over here that gamma, our third root, is equal to 1/3. So we now need to plot the 3 minus 2 root 2i, the 3 plus 2 root 2i, and the gamma on an Argand diagram. First of all, we've got our axis over here. We've got the real axis and the imaginary axis. We can show this 1/3. So that goes here somewhere. So let's just show that. So here we've got the 1/3, 0. And then we've also got the other two roots, 3 plus minus 2 root 2i. So if we show those as coordinates, we have one of the roots over here somewhere. So let's just join this up with a straight line. So the coordinates here are 3, 2 root 2. And we've also got the other root over here. So if I plot that as well, we've got this over here. Coordinates 3 minus 2 root 2. Okay, so those are our roots plotted on an Argand diagram. And now for part B of the question, we have to find the values of p and q. To find the value of p, we can use equation 1, and to find the value of q, we can use equation 3. So if we use equation 1, the sum of the roots, so for part B, using equation 1, we've got the sum of the roots, 3 minus 2 root 2 I plus 3 plus 2 root 2 I. So we've got alpha, beta, and we've also got gamma, which is this 1/3. And all of this is equal to minus p over 3. So here, the minus 2 root 2i and the plus 2 root 2i cancel. So we've got 3 plus 3, which is 6. So we've got 6 plus the third. This is equal to minus p over 3. So if I multiply through by 3, we've got 18 plus 1 equals minus p. 19 is equal to minus p, and therefore p is equal to minus 19. And now if we use equation number 3 to find out what q is, so using the product of the roots, from equation 3, we've got 3 minus 2 root 2 I, so that's alpha, multiplied by beta, which is 3 plus 2 root 2 I, times by gamma, which is 1/3, and all of this is equal to minus q over 3. And we can use our calculator to simplify all this. So we've got over here this product multiplied by 1/3. So we get 17 over 3. So we've got 17 over 3 equals minus q over 3. And now if we multiply through by 3, 17 is equal to minus q q is equal to minus 17. And knowing the value of p and knowing the value of q, we can say in conclusion, f of z, that's equal to 3z cubed minus 19z squared plus 57z minus 17. Question number 2. For part A of the question, we have to explain why the integral of 1 over x lots of 2x plus 5 with respect to x in between 1 and infinity is an improper integral. Quite simply, the integral being integrated over is bounded in between 1 and infinity. And now for part B, we have to prove that this integral here is equal to a times the natural log of b, where a and b are rational numbers to be determined. Well, first of all, if we consider this 1 over x lots of 2x plus 5, we can rewrite this using partial fractions. So we will consider this bit over here, where we've got the 1 over x lots of 2x plus 5. And if we use partial fractions, this is going to be equivalent to a over x plus b over 2x plus 5. So, if we multiply both sides by x lots of 2x plus 5, we have 1 being equivalent to a lots of 2x plus 5 plus b lots of x. And our goal here is to determine the value of a and to determine the value of b. And we can do that by letting one of the brackets equal to 0. And we need a value of x such that one of those brackets is 0. So for example, when x is equal to 0, on the left hand side we have 1, and on the right hand side the b term disappears, we're left with 5a. So therefore, you can see here, a is equal to 1/5. Similarly, when x is equal to minus 5 over 2, we have 1, which is equal to minus 5 over 2b, because the a bracket disappears, and therefore b is equal to minus 2/5. And knowing the values of a and b, we can rewrite this right hand side. So therefore, 1 over x lots of 2x plus 5, that's equivalent to a over x. So here we've got 1 over 5x minus 2 over 5 lots of 2x plus 5. And now we wish to evaluate this integral over here, and we can simply replace this over here with what we've just found over here. So we get this result over here. This integral is equivalent to the integral from 1 to infinity of 1 over 5x minus 2 over 5 lots of 2x plus 5 with respect to x. And at this point, we can factorize out a 1/5. So we've got 1/5 lots of the integral from 0 to infinity of 1 over x minus 2 over 2x plus 5 with respect to x. And for us to evaluate this with these limits here, what we would have to do is replace the infinity with t and then take the limit as t tends towards infinity. So in other words, what all of this is equal to is the limit as t tends towards infinity. We've still got this 1/5, and then our limits now become 1 and t. So we've replaced the infinity with t, and then we've taken the limit as t tends towards infinity. So we're going to evaluate 1 over x minus 2 over 2x plus 5 with respect to x in between these limits, multiply by a fifth, and take the limit as t tends towards infinity. So, continuing with our working, we've got the limit as t tends towards infinity of 1/5. Now here, if I integrate 1 over x, I'm going to get the natural log of x, so we're going to evaluate the natural log of x, and if I integrate minus 2 over 2x plus 5, I'm going to get minus the natural log of the mod of 2x plus 5. So our goal is to evaluate all of this in between 1 and t, and then take the limit as t tends towards infinity. But before we do that, because we're subtracting logs, we can combine these together. So we've got the limit as t tends towards infinity of 1 over 5 multiplied by this result over here, so we've got the natural log of the mod of x over 2x plus 5. And then we wish to evaluate this in between 1 and t. So, if we work all of this out, so for our upper limit, we've got the limit as t tends towards infinity multiplied by 1/5 times by the natural log of the mod of t over 2t plus 5. And for our lower limit, we simply have 1/5 times by the natural log of, well, here on the top we've got 1, and on the bottom we've got 2 times by 1 plus 5, so that's 7 on the bottom. So here we've got 1/5 times by the natural log of 1/7. So, to evaluate 1/5 times the natural log of t over 2t plus 5 as t tends towards infinity, we'd have to divide both the top and bottom by t. So, here we've got the limit as t tends towards infinity of 1/5 times by the natural log of the mod of t over t, and on the bottom we've got 2t over t, and then we've also got this 5 and then we divide this by t as well. And then we've still got this minus 1/5 times by the natural log of 1/7. So we've got the limit as t tends towards infinity of 1/5 times by the natural log of, well, here on the top we get 1, and on the bottom we get 2 plus 5 over t. And then we still subtract off the minus 1/5 times the natural log of 1/7. And you'll notice over here, as t tends towards infinity, this term, the 5 over t, tends towards 0. So we've got 1 over 5 times the natural log of 1/2 minus 1 over 5 times the natural log of 1 over 7. And if we combine these logs together using the subtraction rule of logs, we have over here 1 over 5 times by the natural log of 1/2 over 1/7. So continuing to work all of this out, we'd have over here, in conclusion, 1/5 times by the natural log of 7 over 2. So this is our final answer. Question number 3. We've got figure 1, which shows a sketch of the curve C1 and C2 with polar equations r equals 1 plus sine theta for C1 and r equals 3 lots of 1 minus sine theta for C2. And you'll notice for both C1 and C2, theta is in between 0 and 2 pi. The region R, which is shown shaded over here, lies inside C1 and outside C2, and we have to show that the area of R is p times by the square root of 3 minus q times by pi, where p and q are integers to be determined. And of course here we've got polar equations, we're integrating polar equations, so we'd have to make use of this formula for the area of a sector. So we have 1/2 times the integral of r squared with respect to theta. And of course we've got over here limits of alpha and beta, and we need to determine those values of alpha and beta, and we can do that by solving these two equations simultaneously to find where they intersect in terms of theta. So if we set C1 equal to C2, we've got 1 plus sine theta, and this is equal to 3 lots of 1 minus sine theta. And if we expand on the right hand side, we've got 1 plus sine theta on the left hand side. On the right hand side we've got 3 minus 3 sine theta. So we've got 4 sine theta, which is equal to 2, and you can see here sine theta, that's equal to 1/2, and therefore theta, that's going to equal pi over 6 and 5 pi over 6. And the reason we get the 5 pi over 6, of course, 180, or in other words pi, take away pi over 6, gives the 5 pi over 6. So the area we want is the difference between the area in C1 and the area in C2. So for the area, that's going to be given by, using that formula, 1/2 times by the integral between pi over 6 and 5 pi over 6 of 1 plus sine theta squared d theta minus 1/2 times by the integral between pi over 6 and 5 pi over 6 of 3 lots of 1 minus sine theta and all this is squared. So if we factorise out a 1/2 as a common factor, we've got 1/2 times the integral between pi over 6 and 5 pi over 6 of 1 plus sine theta squared minus, now here, 3 squared, that's 9. So we've got 9 lots of 1 minus sine theta all squared. So we need to deal with the bit inside the bracket. And if we do that, we just have to simply expand and simplify. So we've got 1/2 times by the integral between pi over 6 and 5 pi over 6 of this bit inside the big bracket, so we've got 1 plus 2 sine theta plus sine squared theta minus 9 lots of 1 minus 2 sine theta plus sine squared theta. And our goal obviously is to evaluate all of this in between pi over 6 and 5 pi over 6. So if we multiply the 9 into the bracket, you can see here we've got 1 plus 2 sine theta plus sine squared theta minus 9 plus 18 sine theta minus 9 sine squared theta, and we wish to evaluate this with respect to theta in between pi over 6 and 5 pi over 6, and obviously we still need to multiply by the 1/2. So if we collect like terms, you can see over here we've got minus 8 because we've got 1 minus 9, and then 2 sine theta plus 18 sine theta, that's 20 sine theta, and then minus 9 sine squared theta plus sine squared theta, that's minus 8 sine squared theta. So we need to evaluate this in between pi over 6 and 5 pi over 6. And if I multiply the half into here, we've got the integral between pi over 6 and 5 pi over 6 of minus 4 plus 10 sine theta minus 4 sine squared theta with respect to theta. And for us to integrate sine squared, we would have to recognize over here that cos of 2a, that's equivalent to 1 minus 2 sine squared a, and therefore sine squared a, that's going to be equivalent to 1/2 lots of 1 minus cos of 2a. And we can replace therefore the sine squared theta with 1 half lots of 1 minus cos of 2 theta. So if we do that, we've got minus 4 plus 10 sine theta minus 4 times by 1/2 lots of 1 minus cos 2 theta. And of course, we wish to evaluate this in between pi over 6 and 5 pi over 6. So if we tidy the bit inside the bracket, here we've got minus 4, and then we've got minus 4 times by half times by 1, that's minus 2. So minus 4 minus 2, that's minus 6. And then we've got the 10 sine theta, and then the minus 2 times by the minus cos 2 theta, that's positive 2 cos 2 theta. So we will be integrating this result over here with respect to theta in between pi over 6 and 5 pi over 6. So if we work all of this out, integrating minus 6, we end up with minus 6 theta. Integrating 10 sine theta, we end up with minus 10 cos theta. And integrating 2 cos 2 theta, we end up with sine 2 theta. So we wish to evaluate this in between pi over 6 and 5 pi over 6. And our next goal is to simply work all of this out by substituting in our limits. So if we do that, if we substitute in for the upper bracket, we've got minus 6 lots of 5 pi over 6 minus 10 times by the cosine of 5 pi over 6 plus the sine of 2 times by 5 pi over 6. So this over here is our upper limit, and for our lower limit we've got minus 6 times by pi over 6 minus 10 times by the cosine of pi over 6 plus the sine of 2 times by pi over 6. So if we evaluate all of this, we've got minus 6 times by 5 pi over 6, so that's going to be minus 5 pi. And if we deal with these terms here, we've got minus 10 times by the cosine of 5 pi over 6 plus the sine of 2 times by 5 pi over 6. So it turns out we get 9 root 3 over 2. So here we've got 9 over 2 root 3. And then for the lower limit, we've got minus 6 times by pi over 6. That's just going to be minus pi. And then for the other terms, if we replace this 5 pi over 6 with pi over 6, it turns out here we get minus 9 root 3 over 2. So we have minus 9 over 2 root 3. And if we combine these terms, well here, minus 5 pi minus 5 pi, that's going to be minus 4 pi. And then 9 over 2 minus 9 over 2, that's going to be plus 9. So we have plus 9 root 3. And you can therefore see that the value of P, that's going to equal 9. And the value of Q, that's going to equal 4. So if we go back to the question, you can see that's in the required form. So P is equal to 9 and Q is equal to 4. Question number 4. The plane pi1 has equation R equals 2i plus 4j minus k plus lambda lots of I plus 2j minus 3k plus mu lots of minus I plus 2j plus k, where lambda and mu are scalar parameters, and we have to find a Cartesian equation for the plane pi1. So for us to find a Cartesian equation, we need to recognize that a Cartesian equation will be of the form R dot product with n equals d. And recognizing that R is equal to the column vector x, y, z, we need to find the normal vector n, and we also need to find this value d. So I think it will be a good idea for part A of the question to sketch the plane. So we have our plane here. We have R equals A plus lambda lots of B plus mu lots of C, where hopefully here you can see A, that's equal to 2i plus 4j minus k, B, that's equal to I minus 2j minus 3k, and C, that's equal to minus I plus 2j plus k. So I think at this point it will be a good idea to write the vector in column notation. So we've got R equals this vector A, which is 2, 4, minus 1, plus lambda lots of that vector B. So we have 1, 2, minus 3, plus mu lots of this vector C. So we have mu lots of minus 1, 2, and 1. So what we can now do is find the normal vector from this and then find out the value of d. So our goal first of all is to find the normal vector. So the normal vector is shown over here. So this is the normal vector, and the normal vector we can find by multiplying this vector B with this vector C. So the normal vector n, that's equal to this vector B 1, 2, minus 3 multiplied by minus 1, 2, 1. So if we multiply these together, of course we can use our calculator, so we can go to the vector mode. We will define vector A to be 3 dimensions with components 1, 2, and minus 3. We will now define vector B 3 dimensions with components minus 1, 2, and 1. And then multiplying A by B, you'd find the normal vector n, that's equal to 8, 2, and 4. So, knowing that our normal vector is equal to 8, 2, 4, we can now find out what the value of d is. And over here, d, that will equal A dot product with n. So we have the vector A 2, 4, minus 1, that's here. Dot product with n, we've just found n to be 8, 2 and 4. So if we work out this dot product, we've got 2 times by 8 plus 4 lots of 2 plus minus 1 lots of 4. So if we work all this out, we have 16 plus 8 minus 4. You'd find that to be 20. And therefore, knowing d, knowing n, we can therefore conclude in column notation, the Cartesian equation, we have x, y, z, so this corresponds to r, dot product with our normal vector 8, 2, 4, and this is equal to d, which is 20. And if you want, you can rewrite this as, by taking the dot product, 8x plus 2y plus 4z equals 20. You can also rewrite this by dividing each term by 2, so we have 4x plus y plus 2z equals 10. So this is our final answer in Cartesian form. So everything I've mentioned, that's highlighted in the formula book as well. And now for part B of the question, the line L has equation x minus 1 over 5 equals y minus 3 over minus 3 equals z plus 2 over 4, and we have to find the coordinates of the point of intersection of L with the plane pi 1. And I think it's easier if we express this Cartesian equation in vector form. So we've got x minus 1 over 5 equals y minus 3 over minus 3 equals z plus 2 over 4, and this in vector form. So in vector form, we have r equals, well, here we take the opposite sign of what's after the variables x, y and z, so here we've got 1, 3, minus 2, plus some parameter t, lots of whatever is on the bottom, 5, minus 3, 4. And we can therefore compare this with our plane over here by simply recognizing that the plane meets the line when 1 plus 5t, 3 minus 3t, minus 2 plus 4t, dot product with 8, 2, 4, equals 20. So if we expand and simplify all this by taking the dot product, we have here 8 lots of 1 plus 5t plus 2 lots of 3 minus 3t plus 4 lots of minus 2 plus 4t, and all this is equal to 20. And I can divide each term by 2, and if I do that, I get 4 lots of 1 plus 5t plus 1 lots of 3 minus 3t plus 2 lots of minus 2 plus 4t equals 10. And at this point we can expand and simplify, so we've got 4 plus 20t plus 3 minus 3t minus 4 plus 8t equals 10. If we collect like terms, 20t minus 3t plus 8t, that's 25t. And on the left hand side we've got 4 plus 3, which is 7, minus another 4, that's just 3. So 10 take away 3, that's 7. So 25t, that's equal to 7, and therefore t, that's equal to 7 over 25. So what we can now do is simply find the coordinates by substituting back into our line L over here. And if we do that, x, y, z, that's going to equal 1, 3, minus 2, plus 7 over 25 lots of 7 over 25 lots of 5 minus 3, 4. So if we work all of this out, we can use our calculator. So we have 7 over 25, and if I store this into A, we have 1 plus 5 lots of A, which is 12 over 5. So that's the x coordinate. Next we have 3 minus 3a, so that's 54 over 25. And finally we've got minus 2 plus 4a, which is minus 22 over 25. So we can therefore conclude our coordinates, we've got 12 over 5, 54 over 25, and minus 22 over 25. So if we call this coordinate P, and if we go back to our diagram, we've got our line L which intersects this plane. It would of course intersect at this point P as shown over here. Now for part C of the question, the plane pi 2 has equation r dot product with 2i minus j plus 3k equals 5, and we have to find to the nearest degree the acute angle between the plane pi 1 and pi 2. So the acute angle, that's cos theta equals n1 dot product with n2 over the magnitude of n1 times the magnitude of n2, and we need to make sure we've got positive values for this. Now we know already that n1, that's equal to 4i plus j, rather n1, that's equal to 8i plus 2j plus 4k, and we also know n2, if we go back to the question, that's 2i minus j plus 3k. So n2, that's equal to 2i minus j plus 3k. So we can first of all find the magnitude of n1. So the magnitude of n1, that's equal to 8 squared plus 2 squared plus 4 squared square rooted. So if we work all of this out, we've got 8 squared plus 2 squared plus 4 squared, and then square root this, that's equal to 2 root 21. So we've got 2 times by the square root of root 21. And we can do a similar thing for the magnitude of n2. That's equal to 2 squared plus minus 1 squared plus 3 squared, all square rooted. So if we work this out, we got 4 plus 1, that's 5, plus 9, that's 14, so we've got the square root of 14. We can now find out the dot product of n1 and n2. So n1 dot product with n2, that's equal to 4i plus j, sorry, where am I getting 4 from? That's equal to, rather, 8i plus 2j plus 2j plus 4k dot product with 2i minus j plus 3k. So we have over here 8 times by 2 plus 2 times by minus 1 plus 4 times by 3. So we've got 16 minus 2, that's 14, plus 12, turns out we get 26. So therefore, substituting into this formula over here, and noting all these values are positive, we've got cos theta equals 26 over 2 times by the square root of 21 times by the square root of 14. And if we solve for theta, giving our answer to one decimal place, sorry, to the nearest decimal, to the nearest value, we have the inverse cos of 26 over 2 times by the square root of 21 times by the square root of 14. It turns out we get 41 degrees to the nearest degree. Question number 5. Two compounds, X and Y, are involved in a chemical reaction. The amount in grams of these compounds t minutes after the reaction starts are X and Y respectively, and are modelled by the differential equations dx over dt equals minus 5x plus 10y minus 30 and dy over dt equals minus 2x plus 3y minus 4. And for part A of the question, we have to show that d squared x over dt squared plus 2 lots of dx over dt plus 5x equals 50. So to do this question, if I call this first equation equation 1 and this second one equation 2, if we consider equation 1, we can differentiate it with respect to t, and the reason I want to do that is because in this show that question we have a d squared x over a dt squared, and that can be obtained by differentiating dx over dt with respect to t. So for part A, from equation 1, if we differentiate the dx over dt with respect to t, well, differentiating dx over dt, we end up with d squared x over dt squared. And if we differentiate the minus 5x with respect to t, we can differentiate that implicitly. So we get minus 5 lots of dx over dt. And if we differentiate the 10y implicitly, we get 10 lots of dy over dt, and that's all we have to do to differentiate dx over dt with respect to t. But you'll notice in the show that we've got nothing containing a y, but over here we've got a dy over dt which we need to get rid of. So if I call this equation 3, we already know what dy over dt is. That's minus 2x plus 3y minus 4. So we can substitute in equation 2 into equation 3. So if we substitute in equation 2 into equation 3, we have d squared x over dt squared equals minus 5 lots of dx over dt plus 10 lots of dy over dt, which we now know is minus 2x plus 3y minus 4. And if we expand all of this out, we have minus 5 dx over dt minus 20x plus 30y minus 40. So therefore you can see here d squared x over dt squared is equal to minus 5 lots of dx over dt minus 20x plus 30y minus 40. But you'll still notice over here we've got something involving a y, and in our show that we don't want anything that contains a y. And the way we can get rid of this y is by taking equation 1 and rearranging for y. So from equation 1 again, if we rearrange for, say, 10y, you'd see over here 10y is equal to dx over dt plus 5x plus 30. So if I call this equation 4 and if I call this equation 5, we can substitute in equation 5 into equation 4, recognizing that 30y is the same as 3 times by 10y. So if we do that, if we substitute in equation 5 into equation 4, we have d squared x over dt squared equals minus 5 lots of dx over dt minus 20x, and the 30y we can rewrite as 3 times by 10y, so we have 3 times by 10y, and 10y over here is equal to this result here, so we have 3 lots of dx over dt plus 5x plus 30. And we've also got this extra minus 40. And now we just have to simplify everything. So, tidying all of this up, we've got minus 5 lots of dx over dt minus 20x plus 3 dx over dt plus 15x plus 90 minus 40. So if we collect like terms, minus 5 dx over dt plus 3 dx over dt, that's minus 2 dx over dt. And then we've got minus 20x plus 15x, that's minus 5x, 90 minus 40, that's 50. So d squared x over dt squared, that's equal to minus 2 lots of dx over dt minus 5x plus 50, and rearranging to put this into our required form, which is shown here, indeed we get d squared x over dt squared plus 2 lots of dx over dt plus 5x equals 50. So let's just call this equation 6 for now, and that's exactly what we wanted to show. For part B of the question, we have to find, according to the model, the general solution for the amount of grams of compound X present at time t minutes. So in other words, we have to solve this second order non-homogeneous differential equation. And the first thing we can do to solve this differential equation is to write down our auxiliary equation. So our auxiliary equation, we have the coefficients on the left hand side 1, 2 and 5. So we have m squared plus 2m plus 5 equals 0. So if we solve this quadratic equation, we've got 1m squared plus 2m plus 5. It turns out we get complex roots. You can see m is equal to minus 1 plus minus 2i. So knowing that we have complex roots, we can therefore conclude our homogeneous equation, we have e to the minus t lots of a times by the cosine of 2t plus b times by the sine of 2t. Now, for our particular integral, we have a constant term on the right hand side, so our particular integral we can find. So for the particular integral, because we have a constant term, let's try xpi equals some constant p. So I now need to differentiate this twice and then substitute into equation 6. So if we do that, we have dx pi over dt, that's just going to be a constant term, 0, and also d squared xpi over dt squared, that's also going to equal 0. So if we substitute all these into equation 6, so let's just write this down. If we substitute into equation 6, we have d squared x over dt squared, so that's 0, plus 2 lots of dx over dt, so we have 2 lots of 0, plus 5x, so we've got 5 lots of xpi, and this is equal to 50, as we see over here. So we've got 5 xpi equals 50, and therefore xpi, that's equal to 10. So the general solution of x, that's going to be the sum of the homogeneous equation plus the particular integral. And therefore we can conclude our general solution, that's going to be equal to our homogeneous equation, which is this result over here, e to the minus t lots of a times by the cosine of 2t plus b times by the sine of 2t plus this extra 10, which is the particular integral. Now for part C of the question, we have to find, according to the model, a general solution for the amount of grams of compound y present at time t. So now we need to solve for y. And we already know from equation 3 what 10y is. So we can use this information to solve for y. Now we know what x is, we've just worked that out in part B. We can use that to figure out what dx over dt is and substitute all of this into equation 5. So if we take a look at this equation here, let's call it equation 7. If we differentiate equation 7, so from equation 7, if we differentiate this, dx over dt, using the product rule, we have u times by v dash, so if I differentiate a cos 2t plus b sin 2t, we end up with 2b cos 2t minus 2a sin 2t, so we have uv dash plus vu dash, so u dash, that's going to be minus e to the minus t, times by this result here, a cos 2t plus b sin 2t. So let's call this equation 8. And what we can do now is substitute in equation 8 into equation number 5 over here. So our next goal is to substitute in equation 8, so this is part C, into equation 5. So we've got 10y. This is going to equal, if I get equation 5 up, dx over dt. So dx over dt, that's all of this result over here. So we have e to the minus t lots of 2b cos 2t minus 2a sin 2t minus e to the minus t lots of a cos 2t plus b sin 2t. And then we've got over here 5x. Now we already know what x is. That's this result over here. So we've got 5 lots of this. So we've got 5 lots of e to the minus t lots of a cos 2t plus b sin 2t plus this extra 10. And we've also got the plus 30 as well. So we're going to add on over here 30. And we can expand and simplify all of this. So 10y, that's going to equal, well, if I take out, well, if I expand this bracket here and take out an e to the minus 2t, sorry, e to the minus t as a common factor, you can see here we've got e to the minus t lots of 2b cos 2t minus 2a sin 2t, and then we've got minus this result here. So we've got minus a cos 2t plus b sin 2t, and then we've got, if I expand this 5 into this bracket, we've got 5a, put it all in the bracket, 5a cos 2t plus 5b sin 2t, so 5 times by this gives me this, And then we've got 5 times by 10, that's 50. And then we've got this extra 30. So we can tidy all this up even more. So we've got 10y, which is equal to e to the minus t. Now if we gather everything that contains a cos 2t, well, we've got 2b minus a plus 5a. Well, minus a plus 5a, that's 4a. So over here, if I open this bracket up, we've got 4a plus 2b times by the cosine of 2t. And then we've got, in terms of signs, minus 2a plus, and then we've got a minus b plus a 5b, so that will be 4b minus 2a sine 2t. And then we've got 50 plus the 50 plus the 30, which is 80. And if we divide both sides by 10, the general solution for y, that will be 1/10 e to the minus t lots of 4a plus 2b cos 2t plus 4b minus 2a times by the sine of 2t. And then 80 divided by 10, that's just 8. So that's the general solution for y. Now for part D of the question, given that x equals 2 and y equals 5 when t equals 0, we have to find the particular solution for x and y. So if we deal with the x first, so we will be using equation 7 for that. So let's just call this equation 8 actually. So for part D, when t equals 0, x is equal to 2. So we will now be using equation number 7 to find out the values of a and b. So using equation 7, we have 2 equals e to the power of 0 lots of a times by the cosine of 2t, so we have the cosine of 0, plus b times by the sine of 2t, so we have the sine of 0, and then plus the 10. So we have 2 equals, well here we've got 1 lots of a plus 10, so you can see a is equal to minus 8. And now when t equals 0, y is equal to 5, so we can use equation number 8. So we have 5 equals 1/10 lots of e to the power of 0, and if we substitute in t equals 0, we have 4a plus 2b times by the cosine of 0 plus times 4b minus 2a times by the sine of 0 plus the 8. So at this point we can tidy this up even further. Of course, the sine of 0, that's just 0, cosine of 0, that's just 1, e to the 0, that's 1. So we have 5 equals 1/10 times by 4a plus 2b plus this extra 8. So 5 take away 8, that's minus 3. So we have minus 3 equals 1/10 lots of 4a plus 2b. So timesing through by 10, minus 30 is equal to 4a plus 2b, and knowing that a is equal to minus 8, minus 30 equals 4 times by minus 8 plus 2b. If we rearrange for 2b, well, here we've got minus 32, so minus 30 plus 32, that's 2. So we've got 2 equals 2b. Of course, b is equal to 1. And now, knowing the values of a and b, we can find out the general solution for x and y. So, for the general solution, the particular solution of x rather, if we take a look at equation number 7, a is equal to minus 8, b is equal to 1. So replacing a and b with those values, the particular solution of x, that's e to the minus t, lots of minus 8 cos 2t plus sine 2t plus the 10. And the particular solution for y, substituting into equation number 8, well, here we've got 4a plus 2b, so we've got minus 32 plus 2, that's minus 30. So here we've got minus 1/10. No, we don't. We've got positive 1/10. E to the minus t, lots of minus 30 cos 2t, and then in terms of signs, we have over here 4b minus 2a, so we've got 4 minus 16, so that will be 20. So we've got 20 sine 2t plus the 8. And if you want, you can expand this 1/10 into the bracket, but I'm not going to do that. Now for part E of the question, a scientist thinks that the chemical reaction will have stopped after 8 minutes, and we have to explain whether this is supported by the model. Well, we know what our we know what our particular solutions are. They are shown over here. So let's see what happens beyond t equals 8. So let's go to our table and plot these two functions. Now on this particular calculator, you can plot two functions. So we have over here x, which is equal to e to the minus x, lots of minus 8 cos 2x plus, yes, in a bracket, so here we've also got sine of 2x plus the 10, and the other function we've got 1/10, so that's 0.1, e to the minus x, lots of minus 30 cos of 2x plus 20 sine of 2x plus 8. So if we start at say 7 and finish at 20, and let's go up in 0.5s, if we take a look over here, so let's just get a pop-up display to illustrate what's going on. You can see here, if I say f of x is this and g is this, if we scroll through the values, you can see the values are approximately 10 and 8 beyond t equals 8. So we can conclude the following. So when t is greater than 0, the amount of compound x and the amount of compound y remain constant at 10 and 8 respectively. We just saw that on the calculator, and this suggests that the chemical reaction has stopped, which supports the scientific question number 6, for part I, we have to prove by induction that for all positive integers n, the sum from r equals 1 to r equals n of 3r plus 1 lots of r plus 2, that's equal to n lots of n plus 2 lots of n plus 3. And our aim over here is to replace everywhere where we see an n with k plus 1. So, if we replace everywhere with a n with an k plus 1, we've got k plus 1 lots of k plus 1 plus 2 lots of k plus 1 plus 3. We've replaced everything with an n with a k plus 1, and this is what we want to show somehow. So with a proof by induction question, the first thing we do is we see what happens when n is equal to 1. So on the left hand side we have the sum from r equals 1 to 1 of 3 times by 1 plus 1 lots of 1 plus 2. So over here we get 4 lots of 3, which is 12. And on the right hand side we have, when n is equal to 1, we have 1 lots of 1 plus 2 lots of 1 plus 3. So over here we have 1 times by 3 times by 4, which is 12. And what we see over here, the left hand side is equal to the right hand side. We can conclude that the statement is true for n equals 1. And our next step is to assume that the result is true for n equals k. So assuming that the result is true for n equals k, the sum from r equals 1 to r equals k of 3r plus 1 lots of r plus 2, that's equal to k lots of k plus 2 lots of k plus 3. All we have done over here is replaced on the left hand side and the right hand side n with k. And now our next step is to try and see what happens for n equals 1. So trying the result for n equals k plus 1, the sum from r equals 1 to r equals k plus 1 of 3r plus 1 lots of r plus 2, that's equal to the sum from r equals 1 to r equals k of 3r plus 1 lots of r plus 2 plus the k plus 1th term. So for the k plus 1th term we simply replace on the left hand side r with k plus 1. So we have over here 3 lots of k plus 1 plus 1 lots of k plus 1 plus 2. And with this result over here, we want to show that this all simplifies to k plus 1 lots of k plus 1 plus 2 lots of k plus 1 plus 3. Now, if we use our assumption step and replace this result over here with what we have here, we have k lots of k plus 2 lots of k plus 3, and then we've got the terms here, 3 lots of k plus 1 plus 1 lots of k plus 1 plus 2. So if we expand and simplify over here, we have 3 lots of k, which is 3k, 3 times by 1 plus this extra 1, that's 4, and here we have k plus 3. So we have k lots of k plus 2 lots of k plus 3 plus 3k plus 4 lots of k plus 3. And if we factorise out k plus 3, we have k plus 3 lots of k lots of k plus 2. That simplifies to this result here. And then we have an extra 3k plus 4. And expanding the k plus 3 with the 3k plus 4 gives this result here. So if we tidy all of this up, we have k plus 3, and inside this bracket over here we've got k times by k, that's k squared, k times by 2 plus 3k, that will be 5k, and then we've got over here this extra 4. And k squared plus 5k plus 4 we can factorise, and if we factorise it we end up with k plus 1 lots of k plus 4. So we have over here k plus 3 lots of k plus 1 lots of k plus 4. And if we pay attention to what we want to show, indeed that's the same as this result over here. So we have the k plus 1 multiplied by the k plus 3, which I'm going to write as k plus 1 plus 2, multiplied by k plus 4, which I'm going to write as k plus 1 plus 3. So for our conclusion step, we have the following. See that if the statement is true for n equals k, then it has been shown to be true for n equals k plus 1, and as it is true for n equals 1, the statement is true for all positive integers n. And now for part B of the question, we have to prove by induction that for all positive odd integers n, f of n equals 4 to the power of n plus 5 to the power of n plus 6 to the power of n is divisible by 15. So we have f of n which is equal to 4 to the n plus 5 to the n plus 6 to the n. We want to show that this result is divisible by 15. So as always, we begin with seeing what happens when n is equal to 1. So f of 1, that's equal to 4 to the power of 1 plus 5 to the power of 1 plus 6 to the power of 1, 4 plus 5 plus 6, that is indeed 15. So therefore we see that the statement is true for n equals 1. And now we will assume that the result is true for n equals 2k plus 1. So the reason we want to assume that the result is true for n equals 2k plus 1 is if you go back to the questions specifically said prove that for all positive odd integers n, and odd integers are of the form 2k plus 1. So with our assumption step, we will assume that f of 2k plus 1, so that's going to equal 4 to the power of 2k plus 1, plus 5 to the power of 2k plus 1, plus 6 to the power of 2k plus 1. This result over here is divisible by 15. And we need to try the next odd integer above this, so we now need to try and see what happens for n equals 2k plus 3. And of course we add 2 to the 2k plus 1 to get the 2k plus 3. So f of 2k plus 3, that's equal to 4 to the power of 2k plus 3 plus 5 to the power of 2k plus 3 plus 6 to the power of 2k plus 3. And we want to somehow show that this is all divisible by 15. Now we need to make this result over here similar to what we have over here. And if we do that, we have 4 to the power of 2k plus 3, which we can rewrite as 4 to the power of 2k plus 1 plus 2. Of course, the 1 plus the 2 gives the 3. And similarly, we've got 5 to the power of 2k plus 1 plus 2. And we've also got 6 to the power of 2k plus 1 plus 2. So, what we will now do is use the laws of indices to simplify each of these. So we've got 4 to the power of 2k plus 1, lots of 4 to the power of 2, and of course, multiplying with the same base, we add the powers. And similarly, we've got 5 to the power of 2k plus 1, lots of 5 to the power of 2. And we've also got the 6 to the power of 2k plus 1, lots of 6 to the power of 2. So if we simplify all this, we have 16 lots of 4 to the power of 2k plus 1 plus 25 lots of 5 to the power of 2k plus 1 plus 36 lots of 6 to the power of 2k plus 1. And you'll notice over here, if we compare what we have over here with what we have over here, we can make this result similar to this result over here by first of all taking out a 16 as a common factor and writing this result down. So we have 4 to the power of 2k plus 1 plus 5 to the power of 2k plus 1 plus 6 to the power of 2k plus 1. And then over here, we've got 16 lots of 5 to the power of 2k plus 1, but here we've got 25 of them, so we need to add on an extra 9 lots of 5 to the power of 2k plus 1. And then we've got 16 lots of 6 to the power of 2k plus 1. We've got 36 of them, so we need to add on an extra 20 lots of 6 to the power of 2k plus 1. So, we need to now show that this is divisible by 15. And you'd notice over here, this result over here is what we assumed f of k to be. And we said that this was divisible by 15. So, we have here 16 lots of f to the power f of 2k plus 1, and then we've got this 9 lots of 5 to the power of 2k plus 1 plus 20 lots of 6 to the power of 2k plus 1. And we want to show that this bit over here is divisible by 15, so let's just write that down. So we want to show that this is divisible by 15. So for us to do that, well, if you think about it, 9 times by 5, that's 45, that's divisible by 15, and 20 times by 6, that is also divisible by 15. So we can use that information to help show that this result over here is divisible by 15. So we've got 16 lots of f of 2k plus 1, and over here we can rewrite the 5 to the power of 2k plus 1 as 5 to the power of 2k, lots of 5 to the power of 1. And then similarly here we've got 20 lots of 6 to the power of 2k, lots of 6 to the power of 1. And over here 9 times by 5, that's 45. So we've got 45 lots of 5 to the power of 2k. And here we've got 6 times by 20, that's 120. So we've got 120 lots of 6 to the power of 2k. And then we still have this over here, the 16 lots of f of 2k plus 1. So the 45 and the 120 are divisible by 15. So if I take a 15 out as a common factor, we've got 15 lots of 3 times by 5 to the power of 2k So this gives the 45 lots of 5 to the power of 2k, and 15 lots of 8 times by 6 to the power of 2k. That gives the 120 lots of 6 to the power of 2k. So we've got 16 lots of f of 2k plus 1, plus 15 lots of 3 times by 5 to the 2k, plus 8 times 6 to the 2k. We know this result is divisible by 15. We also know that this result is divisible by 15. So therefore, the entire thing is divisible by 15. So if true for n equals 2k plus 1, then true for n equals 2k plus 3, that's what we've just shown. And therefore, because it's true for n equals 1, it's true for all positive integers n. Question number 7. A sample of bacteria in a sealed container is being studied. The number of bacteria P in thousands is modelled by the differential equation 1 plus t lots of dp over dt plus p equals t to the half lots of 1 plus t, where t is the time in hours after the start of the study. Initially, there are exactly 5,000 bacteria in the container, and for part A, we have to determine, according to the model, the number of bacteria in the container 8 hours after the start of the study. Well, clearly, over here we'd have to use the integrating factor. But before that, we need to make sure that our differential equation is in an integrable form. And we can do that first of all by dividing both sides of the differential equation by 1 plus t. So, for part A, we have dp divided by dt plus 1 over 1 plus t lots of p, and this will equal t to the half lots of 1 plus t divided by 1 plus t. And of course, the 1 plus t's cancel on the top and the bottom, so therefore dp over dt plus 1 over 1 plus t lots of p is equal to t to the power of 1/2. So we can use the integrating factor method to integrate this first order differential equation. For the integrating factor method, if we have a differential equation in the form dp over dt plus xp equals y, where x and y are both functions of t, this would have a solution of e to the power of the integral of x with respect to t, lots of p, equals the integral of e to the power of the integral of x with respect to t, lots of y, with respect to t plus c, where the integrating factor is e to the integral of x dt. And you can clearly see over here x, that's equal to 1 over 1 plus t, and y, that's equal to t to the power of 1/2. Therefore, using the integrating factor, if, that's equal to e to the power of 1 over 1 plus t dt, and if we integrate 1 over 1 plus t with respect to t, we get the natural log of 1 plus t. So we have e to the power of the natural log of 1 plus t, which is simply 1 plus t. So if we use our general form of the solution of the differential equation, we have over here the integrating factor 1 plus t lots of p. This is equal to the integral of the integrating factor 1 plus t lots of y, which is t to the power of 1/2 with respect to t, plus c. And now we can use this to find a general solution of p. So we have 1 plus t lots of p, and this is equal to the integral of, if we expand this out, 1 times t to the half, that's t to the half, t times by t to the half, that's t to the power of 3/2. And we will integrate this with respect to t, and don't forget we have a constant of integration c. So we have 1 plus t lots of p, and if we integrate t to the half, add 1 to the power, divide by the new power, we have 2/3 t to the power of 3/2. And if we integrate t to the power of 3/2, add 1 to the power, divide by the new power, we end up with 2/5 t to the 5/2. And then we add on a constant of integration c. Now, when t is equal to 0, p is equal to 5. We know that because initially there are 5,000 bacteria in the container. So initially tells us t equals 0 and p is equal to 5, because remember p is in thousands. So with that, substituting into the general solution here, we have 1 plus 0 equals 2/3 times by 0 to the 3/2 plus 2/5 times by 0. Rather, we have over here 1 plus 0 times by 5, and this is equal to this result plus c. So therefore c is equal to 5. And knowing that c equals 5, we can therefore conclude for our particular solution, we have 1 plus t lots of p equals 2/3 lots of t to the power of 3/2 plus 2/5 lots of t to the 5/2 plus 5. And therefore p is equal to, if we divide through by 1 plus t, we have 2/3 t to the 3/2 plus 2/5 t to the 5/2 plus 5, and then we divide this entire thing by 1 plus t. So this is our particular solution for the general equation. And if we go back to the question, we need to find the number of bacteria after 8 hours after the start of the study. So that's when t is equal to 8. So when t is equal to 8, p, that's equal to 2/3 times by 8 to the power of 3/2 plus 2/5 times by 8 to the power of 5/2 plus 5, and then we divide all of this by 1 plus 8. So if we work all of this out, we have 2/3 times by 8 to the power of 3/2 plus 2/5 times by 8 to the power of 5/2 plus 5, divided by 1 plus 8, it turns out we get 10.27, etc. And therefore the number of bacteria after 8 hours is 10277. The reason for that, P is in thousands. Now for part B of the question, we have to find, according to the model, the rate of change of the number of bacteria in the container 4 hours after the start of the study. Now, the fact that it says rate of change suggests to us we need to differentiate. So we need to differentiate our function P over here. And that will help us determine the rate of change. Now, of course, over here, to differentiate P, we would have to use the quotient rule. So you can see U, that's equal to what's on the top, 2/3 T to the 3/2 plus 2/5 T to the 5/2 plus 5. U dash, that's equal to, well, if we differentiate this with respect to T, if we differentiate 2/3 times T to the 3/2, we end up with T to the 1/2 plus, and then if we differentiate 2/5 T to the 5/2, we end up with T to the power of 3/2, and if we differentiate the 5, we end up with 0. V, that's equal to what's on the bottom, the 1 plus T, and V dash, that's equal to 1. And therefore, using the quotient rule, dP divided by dt, that's equal to V, that's 1 plus T, times by U dash, which is T to the 1/2 plus T to the 3/2, minus U, which is 2/3 T to the 3/2 plus 2/5 T to the 5/2 plus 5 times V dash, which is 1, and then we divide this entire result by 1 plus T all squared, in other words V squared. Now we're finding out over here, if you go back to the question, the rate of change 4 hours after the start of the study, so we simply substitute in T equals 4. So if we do that, we end up with dP over dt equals 1 plus 4, lots of 4 to the power of 1/2 plus 4 to the power of 3/2 minus 2/3 times by 4 to the 3/2 plus 2/5 times by 4 to the power of 5/2 plus 5. And on the bottom, we have 1 plus 4 all squared. So if we work all of this out, dP over dt, we can simply substitute the 4. So if we do that, we have here 1 plus 4, lots of 4 to the power of 1/2 plus 4 to the power of 3/2 minus 2/3 times by 4 to the power of 3/2 plus 2/5 times by 4 to the power of 5/2 plus 5 all over 1 plus 4 to the power of 2. It turns out we get 403 over 375. Now, you'd notice over here, if we go back to the question, we know that P is in thousands, so we need to multiply this result by 1000. So if we do that, we end up with 1075. So therefore the rate, that would be 1075 bacteria per hour. And now for part C, we have to state a limitation of the model. The number of bacteria increases indefinitely, which is not realistic.